Okay, thank you. And of course, it's a great honor to be here. So I'm going to talk about, what scientists do, trying to understand, or physicists and astronomers trying to understand the basic laws of nature. And surprisingly, science takes all kinds of twists and turns. Surprisingly, string theory has entered this problem in a fundamental way. And I'll end with some discussion of the frontiers. So the search to everybody wants to know why and how the world around us works. And this search has been going on for many centuries. And the most interesting part of it, to me anyway, is there's things that we understand very well, there's things that we can't hope to understand, and then there's those things that are right at the edge, that we might be able to understand, but if we are careful and we choose correctly, but might not. So, as you've been hearing at this festival, there is just an incredible amount that we know about the world around us that was unimaginable centuries ago. We know how, the cookies they gave me in the green room are giving me energy to move around up here. Yet there are incredibly simple questions that a 3-year-old can ask. How did the universe begin? What's inside a black hole? How does the universe end? That we don't have an answer to. So how do we answer these questions? Well, there are many different approaches, and all approaches are needed. But one that has played an important role is a contradiction. So a famous example of this, it comes from Einstein, who wondered what would happen if he held a mirror in front of his face and started running at the speed of light. Would the image disappear or not? He used Maxwell's theory and got one answer. He used Newton-Galileo theory and got another one. So this was a contradiction in the laws of physics, and it was a contradiction in the basic laws of physics that were known at the time. And in order to resolve this contradiction, he came up with an absolutely spectacular insight, which has, of course, been verified in great experimental detail, that in fact, nothing can ever travel faster than the speed of light, thereby avoiding this contradiction. And this completely reorganized our view of space and time. In order to make sense of this, we have to have space and time be part of one SpaceTime Continuum. One can turn into the other. And so it led to a complete change in the way that we view the universe. And in fact, if you look at all the great advances in physics, every one of them had behind them some contradiction of this type. For example, quantum mechanics was born out of a contradiction between the laws of thermodynamics that had been studied in the 19th century and the laws of electromagnetism. You needed a quantum for the electromagnetic field not to explode, and that led to quantum mechanics in 1925, and so on, continuing until today. And what I want to emphasize is that physicists and astronomers are now in the best position imaginable. In the 20th century, there are two kind of pillars of 20th century physics: Einstein's theory of general relativity and quantum mechanics. And wonderfully, it's not a bad thing, it's a wonderful thing, wonderfully, they're incompatible, as we'll discuss. And almost certainly, putting these together will lead us to some very important new insights about the nature of the physical world, on the same scale as the insights that were brought about by quantum mechanics and relativity. So that, of course, is incredibly exciting. The scale for this, though, is not the scale of a National Science Foundation grant, 3 years. The scale is decades or centuries. It was a century from Schwarzschild's discovery of the black hole till Shep saw it last month. That's how long these things take. So let me just say a few words about what general relativity and quantum mechanics are. So Einstein taught us in his general theory of relativity that the force of gravity is an illusion, that what actually happens is that the presence of a mass like the sun or like Shep's black hole curves the space-time around it, and something which wants to go in a straight line actually moves at each point. It's following its nose and going forward, but in the end, the whole arc ends up being a closed orbit. And this Earth orbit around the sun is just like the orbit of light around a black hole that Shep and the Event Horizon team just took a picture of. Now, in quantum mechanics, the basic idea is the uncertainty principle. Another thing that we have believed to be true until the beginning of the 20th century is that there was an absolute notion of position, that had complete, infinite, precise meaning. In quantum mechanics, we learn that that's not true. Anything which is moving must also have some uncertainty in its position, which in general, in the real world, is very small, but when you get down to atomic objects, it can become very large. Now, nothing is immune from the uncertainty principle. So when you put the uncertainty principle together with Einstein's theory of general relativity, you really get in a lot of trouble, because what you learn is that space and time themselves are uncertain. And if you don't know what those words mean, neither do I or anybody else on Earth. We're trying to figure it out. And it's a grand, wonderful, exciting challenge to try to figure this out. And we feel that we're making some progress. Now, those were words. The fact that quantum mechanics and general relativity don't fit together has several aspects. It was first noticed by Pauli in the 50s. There's a machine called quantum field theory for putting together classical theories with quantum theories, coming out with something consistent. This has worked for the weak, the strong, and the electromagnetic interactions. Last time I counted, there were 43 Nobel Prizes that had been given for this over the 20th century. It's been tested to 16 decimal places. It's the most accurate most accurate theory in the history of human thought. It must be correct. But when you apply it to gravity, you get garbage. Okay, so you have to do something about that. Now, there's one attachment that we know of that gives something sensible, but we don't know if it's the attachment that nature ordered or not. Nevertheless, it's been interesting to think about. So the laws of physics that we know are not self-consistent. We have to figure this out. This is something which is at the edge of our knowledge, understanding how Einstein's theory of general relativity and the uncertainty principle can fit together. And it's a very concrete and well-posed problem. And it turns out that black holes somehow, as well as in astronomy, in this line of theoretical reasoning, black holes have come to play a central role. And so what is a black hole? Well, if you're on the Earth, the escape velocity is 11 kilometers per second. You have to jump at 11 kilometers per second. And if you could do that, ignoring air friction, you could just keep going forever, escape the gravitational field of the Earth, and go on out to outer space. On the moon, it's only 2 kilometers per second. There isn't as much mass in the moon. And if you have enough mass in one place, you would have to go faster than the speed of light. Einstein told us that's impossible. So nothing can get out of a region in which there is above some critical concentration of mass energy. Such regions, it seems fantastic. People were reluctant to believe that such regions really exist. I think Shep and the Event Horizon Telescope have vanquished the last holdouts. Now we've really seen them. And that's called, of course, a black hole. That's what a black hole is. Now, black holes were discovered by Schwarzschild in a really unequivocal way by solving the Einstein equations in 1915. But nobody understood what they were. There was 50 years of argument about what this solution meant. And the great man Einstein himself, this is a direct quote from one of his papers in 1939, said that they didn't exist. If he said this in my general relativity class, I wouldn't be able to give him a passing grade. That is not to say Einstein wasn't a very, very, very smart man. It's just that it is really, really, really confusing. And it took 50 years of many of the great minds of the 20th century to figure out what a black hole is. What's a horizon? How do you understand things that orbit around it? How do you make them? What is their behavior? And that problem was eventually solved. For many years, people didn't believe they exist. We had incremental evidence, astronomical evidence that they existed, which got better and better. And now it's all out there in plain view. And so now we know they exist, but they're rather strange objects. The way that we finally understood them is that they are nothing. And when I say nothing, I really mean nothing. Not like as in this room where there's air, or outer space where there's no air. There's a sense in which a black hole is the edge of space. There isn't even anything inside it. And moreover, they are featureless. They're the simplest objects in the universe. It's not like a star, where if you have two stars of the same size and brightness, they still differ in myriad different details, different compositions, molecules moving around in different ways, and so on. Every star is different in many, many ways. But black holes are purported to be rather different. All black holes of the same mass and spin are supposed to be exactly the same. And John Wheeler, who also invented the word black hole, characterized this by saying that black holes have no hair. So hair is a feature on an object. Some is longer, some is shorter. You can cut it, you can comb it different ways. Something on the outside of our heads. And in that sense, there's nothing outside, on the outside of a black hole, that can distinguish it. And this is rather curious that the universe should contain such objects, such very simple, pure, fundamental objects. Now, just when we thought we'd finally understood what a black hole was, Stephen Hawking threw a monkey wrench into the works. And the way he did this was by saying, well, you know, the world is described by quantum mechanics, not classical mechanics. Einstein's equations were classical equations. There's no uncertainty principle in the equations that Schwarzschild solved. And the uncertainty principle has no exceptions. Everything must be subject to the uncertainty principle. It would be mathematically inconsistent to have some objects get a pass that they don't have to obey the uncertainty principle. And that includes black holes. And what Stephen Hawking found is that the horizon, one way of describing it, though of course they're precise equations, one way of describing it is that the horizon itself is subject to some uncertainty in its position. And that enables things which were inside to, at a very slow rate, to kind of slip out. And so, in fact, black holes, according to Hawking, are not completely black. They radiate at a temperature, and here's the formula for the temperature, which a very important formula in modern physics, and now inscribed on his stone in Westminster Abbey. So black holes aren't black. They radiate due to quantum mechanical effects. Now, they obey a law, a so-called law of thermodynamics, which tells you how hot the radiation is as a function of the mass of the black hole. Now, in the 19th century, the people had measured the behavior of many different kinds of systems: water, oil, carbon, gases, and they measured how their temperature would change as you change the pressure or the volume that they're in, or put it on a burner, measured the properties of their materials. And one of the really stunning, beautiful advances in science in the 19th century was Boltzmann's discovery that the so-called laws of thermodynamics follow from what was then a hypothetical theory that matter is composed of individual molecules. And then you can use statistical reasoning to derive the laws of thermodynamics, which become secondary laws. And so if you know, Boltzmann explained to us that if you know how the temperature depends on the mass, you know how much structure there is inside of something. You know how many molecules there are and how many different ways they can move. So in a manner following Boltzmann, Hawking's formula was used. It's known the Bekenstein-Hawking formula. Bekenstein was also involved in these developments. So we have a formula for how many gigabytes, how much stuff there is in a black hole. And it's proportional to the area of the black hole. and there is an important factor of 4, Newton's constant, which measures the strength of gravity, and Planck's constant, which measures the strength of quantum mechanics. So this is a very striking universal formula which ties together many different branches of physics: gravity, quantum, statistical mechanics and thermodynamics, general relativity. Very mysterious formula, and we don't understand we know that it must be correct. Hawking gave consistency argument that this must hold, but we don't really understand why it's true. Now, before I get on to that, I want to say that this is a huge number. All the data in the Google data banks would fit inside a tiny black hole, a trillionth of a trillionth of a millimeter. And in fact, we have reason to believe that this is a fundamental bound, that it is a law of nature, that there's a maximum on how much information you can cram into a region of a given size. You can derive contradictions if you had something which would violate this bound. And so we think that, in fact, that black holes are the best storage information devices in the physical universe. And this is going to be trouble for Moore's law, because Moore's law says that if you have a chip of a given size, every few years you can double the amount of information that you can put on that chip. But if you put the numbers in, you find that after 300 years, your chips will become black holes. Okay, now if you've been paying attention, I've told you two things which seem completely at odds with one another. One is that a black hole is the simplest object in the world, characterized by Wheeler's phrase, "a black hole has no hair." The other is that, according to Hawking, they're the most complex objects in the world. And so how is it that these opposite descriptions of black holes can be consistent? This is a huge paradox for physics, and one that sat there for many decades, and then we got some insight into it from string theory. Now, string theory, we don't know if string theory describes the real world or not, but we do have, I would say, as overwhelming evidence that it describes some universe, some mathematical system, which at least lives in the mind, which is self-consistent and contains both quantum mechanics and general relativity. And it's a world, whether or not it's our own, in which we have a fantastic amount of control over the equations. And we can ask the question, how does string theory resolve this paradox? String theory is a theory which purportedly unifies quantum mechanics and general relativity. It must find some solution to this paradox, and if it doesn't, it's dead. And so we investigated this problem, and we found that indeed there was a method within string theory of counting all the gigabytes that are in certain kind of black hole. And it exactly agreed, including the factor of 4 and in many more details that I can't describe, with all the predictions that Hawking made. So we had one context in which this puzzle has a complete resolution. And I should mention that that an important ingredient in this argument is something called conformal symmetry. It's a special symmetry that some black holes have, which enable us to do the calculation. Now, when we did the calculation, it was a long, difficult calculation, which took many pages, used a lot of detailed properties of string theory and a branch of mathematics called algebraic geometry. And it all seemed a very special situation occurring in string theory. But as time went on, we learned that the details of string theory were not really essential, that we could develop more and more simplified arguments. And the simplified arguments really only depended on this conformal symmetry. And in fact, conformal symmetry is present in some black holes which are very rapidly spinning. And so we can sort of throw out the string theory, but keep the trick that string theory uses to reconcile the maximally simple and the maximally complex pictures of black holes with one another. And this works for very rapidly spinning black holes. We don't know what the spin of the black hole is, but there are a number that have been observed that have this very rapid spin. And we are in, so here's a picture of a black hole. This is more like GRS 1915, one in our own galaxy, fed by a nearby companion star, and matter bleeds off, circles around the black hole. And the symmetry, the jets coming out of the poles of the black hole is sitting there, and the symmetry acts in this little region here, which is the horizon of the black hole. And that is where all the gigabytes are stored. Okay, so we have these theoretical reasonings and these pictures of how we might resolve this contradiction between quantum mechanics and general relativity. But we're physicists, and we'd like to connect it in however remote a fashion with things that are being observed. And in particular, we'd like to know what the consequences are of this conformal symmetry, which will be present if M87 turns out to be rapidly spinning. And there is a suggestion that M87 could be rapidly spinning, because rapidly spinning black holes often have long jets like M87 does. And I want to say that it's a wonderful and really truly historic development that after 100 years of thinking about black holes, that just in the last month, we've seen one. And it brings all of these investigations, it gives them a further sense of reality. So here's pictures of Shep's array. Here is a picture of M87, which they were trying to image. And here's what they actually saw. And so in discussion with the Event Horizon team, we're now looking at how would we see in this donut and in more highly pixelated versions, which will appear in the future, how will we test for this conformal symmetry? And there's more data to be released, and this is something we're very excitedly working on. Here's a prediction which we've published about the polarization profile. The data which will be out in the next year, which would be a signal of this conformal symmetry, which is the key to reconciling the puzzle raised by Hawking. Now, not all black holes have spin. And the puzzle is there for all black holes. The spin and the conformal symmetry is a tool that we used, and we'd like to understand all black holes. And there have been some very recent interesting developments on this. So I told you about how black holes have no hair. In fact, they have a very subtle form of hair, and this has been understood in the last few years by Stephen Hawking, Malcolm Perry, and myself, and there have been many other follow-up papers on it. And I don't have enough time to go into a detail, but I just want to say it all follows from a careful application of Einstein's equivalence principle. So the equivalence principle says that if you're in an elevator with rocket jets on the bottom in outer space, that is the same, there's no difference between that. And what you mean by saying there's no difference turns out to be a very subtle thing. But the simplest approximation to that is that there's no experiment that you could do in the elevator, if the elevator isn't too big, between an elevator with rocket jets in outer space or an elevator on the surface of the Earth, feeling the force not from the acceleration, but the force from the Earth's gravitational pull. Einstein told us this were equal. Now imagine a series of elevators tiling the surface of the black hole, and we want to describe the black hole by an array of elevators and all the measurements in them, including the synchronization of their clocks. And it turns out that understanding when two such configurations are equivalent is more subtle than previously thought. And in fact, there are subtle differences that can be ascertained by subtle observations of this type. And that would give, that imparts what we call soft hair. Hair, the word comes from Wheeler. And the word soft is a word which in physics is used to mean something with very little energy that's hard to detect. And so that is being pursued as a way to understand all black holes, which must have some solution of the problem of quantum mechanics and general relativity. And finally, let me conclude a sense of frustration that scientists feel in trying to talk about this because some of the things are so specialized. I feel a little bit like somebody who went out and discovered the Grand Canyon and the beautiful rock formations and so on, and then came back and was trying to describe it. Well, now we've got one picture, but from Shep, but trying to describe it just in words without any photos, it's hard. The equations are incredibly beautiful, but it takes a long time to learn them. And this was the best I could do in an hour. In conclusion, the road to increase our understanding, to move a little bit beyond the edge of our current knowledge, is full of surprises. It never goes the way we think it's going to go. We start out to try to understand one thing, and we learn about something else, but it's full of twists and turns, but we don't know where it's going, but it's pretty clear we're going forward. Thank you.